Hello all. This is a video I have been preparing for some time now. The purpose of this video is to discuss how to solve the one-dimensional Schrodinger equation for a somewhat complicated potential, which is the Poschl-Teller potential that I wrote here on the title. And we will do this using three different approaches. We will find the direct solution, and in the parentheses I wrote 1930s because this is when this potential was introduced by Poschl and Teller back in the day. Okay, this potential. This potential was introduced to describe, as far as I know, molecular vibrations. Okay, but we won't talk about that. We will focus on solving the equation itself. So this potential was introduced in the 30s, around the time when quantum mechanics was taking shape. Okay, but solving differential equations similar to the Schrodinger equation was something that people knew how to do since the 1800s at least, because as we will see, this reduces to the Legendre equation, the associated Legendre equation. So this was kind of common knowledge at the time. Okay. We will then solve the same exact equation using matrix diagonalization, which involves expanding the wave function, this thing. We will talk more about it in a while. So we will expand it in a harmonic oscillator basis. We will talk about what that means and how to do it, okay? And I wrote 20th century because it was also introduced, I mean, this kind of method of finding of approximating a function using a basis expansion in quantum mechanics was introduced in the 20th century. I'm sorry for the mumbling. But again, this was something that people did and knew how to do since, again, the 18th century, because back then people were able to use Fourier analysis to solve differential equations, which is a very similar thing, pretty much, okay? And finally, we will come to the 21st century, as I say, and talk about how to solve this equation and get the wave function for the ground state only. This is something I found interesting. I read a few papers about it recently. And it's nothing more than PINs, and PINs stands for physics-informed neural networks, okay? Which is a new development in machine learning that allows people to solve differential equations, as you will see. And I wrote 21st century because this is brand new, guys, okay? This is something that was introduced recently, as far as I know, okay? Okay, machine learning is not a totally new thing, and despite what people think, because of this whole AI thing that is going on, etc., people think that it's brand new, but I think AI was introduced in the 1950s, okay? It wasn't very useful due to not having a lot of computational power and so on. But anyway, most of the developments happened indeed within the last 10, 15 years maybe. So anyway, okay, this is the outline kind of the video, okay? And I will probably have to break this into multiple videos because it's too much material. And the goal is to talk about the theory first, okay? So we will write down notes, solve the Schrodinger equation, and discuss whatever it is that is important to discuss, okay? And then in the second part, say, we will show some Python code you can use to play around with these concepts, okay? I wrote a notebook. I will probably just demonstrate what it does because it's going to be difficult for me to just type equations and talk about what the code does, etc. So we'll see. So let's start. And we will start with the direct solution, okay? So let's start with a clean page, and let's write down the Schrodinger equation in one dimension, okay? And this is the time-independent Schrodinger equation, okay? And this video, I guess, is suitable to people who already know some quantum mechanics, though it's not necessary. I mean, it's just a differential equation, if you think about it cynically, okay? Okay. So what does this differential equation tell us? It asks us to do, pretty much. We have to find a function psi of x, for which if we take the second derivative, okay, and add it to the potential multiplied by the function, we should find a constant times the function, okay? This is it. And for the Poschl-Teller potential, v of x is minus lambda times lambda plus 1 over 2 times the hyperbolic secant squared of x, okay? And the hyperbolic secant of x is 1 over the hyperbolic cosine of x. And since we have a negative sign, if you plot this, okay, it will look like this. So this is your x-axis and this is v of x. Let's use a red color. It will look like this, okay? Like a potential well, pretty much, okay? Similar to the harmonic oscillator. We will see how this is related in down the line, okay? So this is what this potential looks like. Lambda is an integer, okay? So lambda is 1, 2, 3, 4, and so on, okay? Let's go to a clean page. And we will work by setting, so we will set h bar equal to mass equal to 1 for simplicity. So we have to solve this equation. Minus 1/2 d squared psi over dx squared minus lambda times lambda plus 1 over 2 times the hyperbolic secant squared x times psi of x, and this should be equal to e times psi of x, okay? We can rearrange this. So we will start solving this equation, okay? This is what I will be doing. For simplicity, we will write this as psi double prime, which means the second derivative, okay, as usual. So we can do this plus lambda times lambda plus 1 times the hyperbolic secant squared plus 2e times psi of x equals 0. Okay, let's call this equation 1. Now, how do we go about solving this? We will make the substitution u equals to tan h x. So we will set the hyperbolic tangent of x is equal to u, okay? So this is our equation 2. And let's work on a few math now. So with this substitution, we have to replace d over dx with d over du times du over dx, okay? So you can see that this makes sense because if we delete this, we get d over dx, okay? So, but let's work this out. We can find du over dx because we are given an expression that connects u and x, okay? So, du over dx is actually equal to the hyperbolic secant h squared, which is 1 minus the hyperbolic tangent squared. This is a property that connects the hyperbolic secant and the hyperbolic tangent. You can check into any math methods book, okay? I'm not going to prove it, I'm just going to use it. So this is what equal to 1 minus u squared, and this is our equation 3. Okay, and another thing that is important to notice is that for x going to infinity, plus infinity, u goes to 1, okay, because of this substitution, okay? And if x goes to minus infinity, then u goes to minus 1. Okay, so u is in the region between minus 1 and 1 included. Okay, so that's 4. Okay, let's keep working. We have an expression for d over dx, which allows us to find what d psi over dx is, which is equal to d psi over du times 1 minus u squared. Okay, simple as that. But the first derivative of the wave function is not what we need. We actually need the second derivative. Okay, and we can do the same thing. This is equal to d over dx of d psi over dx. But we have an expression for d over dx. Okay, so actually let's use the equality symbol. Okay, so this is equal to d over du times d psi over du. Because we already calculated, we can plug this into there. Okay, d psi over du times 1 minus u squared. Okay, and then we need du over dx, right, which we calculated before. So this is equal to d over du d psi over du times 1 minus u squared, and then this is equal to 1 minus u squared. Okay, and we will leave it there because it's gonna be a mess to take this derivative, so we will keep it like that, and you will see why in a moment. So let's call this 5. Okay, now using all these relationships that we find from 1 through 5, we get the following. Actually, let me go to a clean page. Let's erase this. Okay, let's use a clean page. So from 1 to 5, we get d over du of d psi over du. And now the wave function is a function of u, okay? 1 minus u squared times 1 minus u squared plus lambda times lambda plus 1 times 1 minus u squared plus 2e. This is because this is equal to, remember that this is equal to the hyperbolic second h squared, and we substitute that, okay? Times psi equals 0. So we can write this as follows. So we will divide everything with this factor 1 minus u squared, okay? Assuming that u squared is not equal to 1, okay? So we will divide everything to get d over du of 1 minus u squared d psi over du plus lambda times lambda plus 1 plus 2e over 1 minus u squared times psi equals 0. Sorry, I crammed everything in there. Let's try to make some space. Okay, there. Okay, hope this makes sense. So let's call this equation 6. Okay. Now, now comes the reason why I kept this as a first derivative and I didn't expand to get the second derivative. Okay. So let's compare this differential equation. By the way, to solve differential equations, there are various methods. We are not going to get into this in this video because we're going to talk about quantum mechanics, the solutions to these equations, and how you can get the same solutions using basis expansion and machine learning, okay? So compare, this is a familiar equation from differential equations pretty much. So compare 6 to the associated, this is how it's called, to the associated Legendre differential equation. Okay, so this differential equation is written as d over dx of 1 minus x squared d psi over dx plus L times L plus 1 minus m squared over 1 minus x squared psi equals 0. Okay, this is equation 7. Okay, and in equation 7, x goes from minus 1 to 1, okay? Because usually x is cosine of theta, okay? This equation appears when we solve for the radial part of the three-dimensional differential equations. For those of you who are more advanced in quantum mechanics, we're not going to talk about that. We will just take it as is and compare 6 and 7. So let's go back to the equation. As you can see, they are almost identical, except that L should be identified as lambda, and 2E, which is our energy, by the way, okay? Because don't forget, we are trying to solve the Schrodinger differential equation, so E is energy, okay? And 2E is equal to minus m squared. So in our equation 6, so set 2E equals to minus mu squared in 6 to get, I hope all this makes sense, by the way, guys. It's a little bit difficult to describe these things over the internet because you don't have the feedback you get from a classroom, but I will do my best, okay? So lambda times lambda plus 1 minus mu squared over 1 minus u squared times psi equals 0. Okay? And by the way, I forgot to mention that the solution to this equation, equation 7, the solutions are the associated Legendre polynomials of the first and second kind, okay? Because this is a second order linear differential equation. It has two linearly independent solutions, okay? And what do you mean by linear differential equation? All the function and all of its derivatives are in the first power, okay? I mean, there are no terms like psi squared, the first derivative of psi to the cube or something like that, okay? That will be a non-linear differential equation, okay? So E is minus mu squared over 2 with lambda equal to 1, 2, 3, 4, etc. And mu can only be 1, 2, 3, up to lambda. Okay, so this is a consequence of the associated Legendre differential equation. So what do we mean by that is that for a given lambda, so if lambda is say 3, then there are only 3 solutions, 3 states, okay, 3 bound states pretty much. So E will be minus 1 over 2 for mu equals to 1. For mu equals to 2, we will have minus 2. And for mu equals to 3, which is lambda, we will have 9 over 2, minus 9 over 2, okay? Because for lambda equal to 3, mu can only be 1, 2, and 3, nothing else, okay? If lambda is equal to 5, then mu will be 1, 2, 3, 4, and 5, okay? And the ground state is the state with the lowest eigenvalue, okay? So the bound state, the ground state, I'm sorry, because all of these are bound states. So the ground state will have E equals to minus lambda squared over 2, okay? I hope this makes sense. Let's go talk about the solution. Okay, these are the eigenvalues, as they are called in quantum mechanics, okay? Now let's go talk about the eigenfunctions, the wave functions, okay? So the solution to our equation is psi of u equal to some constant c1 times the associated Legendre polynomials of the first kind plus some other constant c2 times the associated Legendre polynomials of the second kind, okay? But recall that u is the hyperbolic tangent of x. Okay, u goes from minus 1 to 1. Now with this substitution, we go back to x, taking values from minus infinity to infinity to get the solution, the final solution, psi of x, because we will substitute u with tanh of x equal to c1 times the polynomials, the Legendre polynomials of the first kind of tanh x plus c2 times the associated Legendre polynomials of the second kind. Okay, now there is the first problem. Remember that our potential looks like this, okay? This is x, this is v of x, this is minus infinity, plus infinity, okay? So this is our potential. So the wave functions should look like something like this, something like a standing wave, and which decays exponentially outside of this potential, okay? So what am I saying? Yes, okay. Imagine this. The green wave function is, it's plotted, it's inside the potential, but actually if, what am I trying to say? I'm trying to say that if we plot the wave function alone, it will look like this. Okay, something like this. But I'm showing it inside the potential, okay? So it should go to 0, like there should be a 0 probability to find the particle at plus or minus infinity, okay? But this solution, the q lambda mu solution, goes to infinity as x goes to infinity. So we have to discard that solution. So if x goes to plus or minus infinity, q lambda mu of the hyperbolic tangent of x goes to plus or minus infinity as well. So we discard those solutions. And our solution, our final solution, is psi, let's call it lambda mu of x equal to c1 times the associated Legendre polynomials of the first kind, with the argument being the hyperbolic tangent of x, okay? is there anything else I want to say? Okay, remember that lambda, the value of lambda defines our potential. So if lambda is, say, 3, we only have 3 such solutions. The ones with mu equals to 1, 2, and 3. If lambda is 5, we have 5 solutions with mu equal to 1, 2, 3, 4, and 5, while lambda is 5. Okay, I hope this makes sense. I will talk further about this later, but let's find a normalization for this. Okay, so in other words, we want to find the value of this C1. Okay, so normalization. So the integral from minus infinity to plus infinity of psi lambda mu of x squared dx must be 1. Okay, so the integral from minus infinity to plus infinity of c1 squared times the polynomials of tanh of x, okay, squared dx must be 1. Okay, but we will again use the substitution. So use u equal to the hyperbolic tangent of x. Okay, so this is going to go in there. And then we have to find an expression for dx, which we did earlier, actually. So dx is du over 1 minus u squared. And the limits of integration go from minus 1 to 1 with this substitution. Okay, these are all things, we are taking advantage of things we used earlier, because remember, where was it? Okay, it's one of my negative traits as a teacher, I guess, because I write too many notes. So there it is. Okay, du over dx is 1 minus u squared, therefore dx is du over 1 minus u squared. Okay, and u goes from minus 1 to 1. Okay, let's go back to the integral. So the integral converts to the integral of c1 squared. Actually, we can take this outside the integral because it's a constant. So c1 squared, the integral from minus 1 to 1 of p lambda mu of u squared over 1 minus u squared times du must be equal to 1. This is a well-known integral. I mean, you can check any tables of integrals. Usually tables of integrals or a book on math methods, you can use, I don't know if, I didn't check Arfken, but Arfken might have a chapter devoted to these polynomials and their identities. You can go online and check the Wolfram Math World page. I usually check that. It has many integrals. And of course, now we also have ChatGPT. You can plug it in and see if it works, though you have to always verify the results that ChatGPT gives you, because sometimes it outputs garbage. But so, I mean, it's getting better, so maybe you can trust it. I don't know. And also Mathematica can give you this. Anyway, the value is so c squared times gamma of lambda plus mu plus 1 over gamma of lambda minus mu plus 1 times mu with mu, sorry, this must be equal to 1 and mu must be larger than 0. Okay, so c is the square root of mu times gamma of lambda minus mu plus 1 over gamma of lambda plus mu plus 1. So this is our constant, and by the way, gamma of x plus 1 is x factorial. So the final answer, oops, the final answer is that for the Poschl-Teller potential, the wave functions are given by this expression. This is equal to gamma of lambda minus mu plus 1 over mu, oops, times mu, I'm sorry, over gamma of lambda plus mu plus 1 times the Legendre polynomials of the hyperbolic tangent of x. Okay, so the holy grail of quantum mechanics is finding this equation. There are not too many potentials for which an exact solution, and by exact we mean given in terms of special functions, functions that are well known and they have a name and stuff like that. So there are not many potentials in 1 dimensions or in 3 dimensions as well, for which an exact solution can be found. The Poschl-Teller potential is one of them. Then, okay, the harmonic oscillator potential is another one. The infinite square well is another one. The shallow potential is another one, though yes, it has exact solutions, but to find the eigenvalues, you have to solve some complicated equation from what I remember. The Morse potential has exact solutions, but it's only a handful of potentials for which we can write the solution in closed form like this, okay? Before we stop talking about the exact solution, and let's go back. I promise that in this video we will see 3 methods of solving this equation, so we are done with this one, the first one, okay? So this is the solution. I'm gonna write a few notes. So note, I mean by notes I mean things that you should be careful with. So the solutions are orthonormal. Oops. Orthonormal within the same lambda. So what I mean is that if we take the integral from minus infinity to plus infinity of y lambda mu of x times y, lambda should be the same, but mu can be different, of x, oops, dx, this should be equal to the Kronecker delta of mu prime, okay? And why is that? Because lambda defines the potential for the Poschl-Teller case, okay? Hence, wave functions with different lambdas, so wave functions with different lambdas are solutions to different potentials. Because recall that v of x is minus lambda times lambda plus 1 over 2 times the hyperbolic secant squared. So if lambda is 3, for example, and you take the wave function of that potential and try to see if it's orthonormal to a wave function for the potential lambda equals 2, that's not going to be true, okay? Be careful with that, okay? So the wave functions are orthonormal within the same lambda only. That's it. This is something we discussed already, but I'm going to write it again. So for a given lambda, there are exactly lambda bound states, which are mu equal to 1, 2, 3, up to lambda, and with energy equal to minus mu squared over 2. Okay? And the final thing is that lambda determines the depth of the potential. Okay, and another thing I haven't mentioned so far, I kind of tricked you, is that since the potential looks like this, remember at some point we made the substitution of 2e equal to minus mu squared. Okay, because minus mu squared corresponds to the bound states. So states that stay within the potential. So states that belong to the negative of the potential axis, the y-axis. If we set 2e equal to mu squared, so plus mu squared, we will find the scattering solutions. So solutions that correspond to a wave coming in, and then it interacts with the potential and does things to it, and then it exits, something like that. Okay, so we focused on the bound state solutions. Okay, I'm gonna erase this. I hope this makes sense. If it doesn't, you can ask me in the comments. I think this is a good point to stop. Okay, so this is the first video which corresponds to the exact solution for the bound states of the Poschl-Teller potential. In the next video, I will discuss the theory behind how you can obtain the same solutions using a basis expansion, and in another video, I'm going to talk about the machine learning approach, and then we will go and see my notebook, the Python notebook that discusses these things computationally. So I hope this is useful. Let me know what you think about it. I plan to make more of these videos. I really like these kind of concepts, quantum mechanics and so on. So yeah, I'm gonna see you in the next one. See you.